All right, good evening. This is April 16th. It's Math 2414. A couple of comments. Homework, your next homework and your last homework assignment. Let me emphasize that your last one for the semester will be due April the 29th. I'll assign some homework next week after the exam. Just a problem or two probably that will be due on April the 29th. And like I said, that will be your last homework assignment of the semester. I have graded everything else. I've uploaded all the grades for all the other assignments, except for the one that you turned in yesterday. That one's not graded yet, but I'll be getting that one graded in the next few days. This week, Monday, today, so you have lecture at 7 o'clock. That's what we're doing right now. Tuesday, tomorrow, online office hours, 11 to noon and 8:30 to 9:30. Wednesday, remember, no lecture on Wednesday, but I will be on campus at the North Harris campus, Winship 115K, from 4 to 6 o'clock. Thursday, I'll be on campus from 9:30 to 11:30 in the morning. So please don't hesitate to come by for help. I'll be happy to help you out. You can actually come by in person and talk to me. I'll be happy to help you. The Exam 3 window opens on Thursday also at April the 19th. It goes through the 24th. And Friday, Saturday, and Sunday, I will make online office hours by appointment. So you just need to email me, and we'll try to come up with a time that's agreeable to both of us. And we can set up an appointment for you either Friday, Saturday, or Sunday of this week. And then I have my regular online office hours on Sunday night from 8:30 to 9:30. Today, a decent part of the beginning of class, we're going to be going back over some of the things that we've been talking about with series. So a lot of this at the beginning is a good review going into Exam 3. Kind of give you a good overview of all the different tests we've talked about. So today, we'll start out by looking at the ratio test and the root test. I talked about the ratio test last time and the root test. So let's see. Remember that the ratio test is going to be on your exam. So that's on Exam 3. And the root test, not on Exam 3. I'm not going to put that on Exam 3. And then, so after we'll go through the ratio and root tests, we'll take one last look at series and convergence, kind of go back over the different tests we've talked about, talk about a few things that you can think about as you're proceeding on with a problem. And then we'll start in on power series, the last topic really that we're going to cover this semester, and talk about series of functions. We've been talking about series of constants, and so with power series, we'll be talking about series of functions and start laying the groundwork for Taylor and Maclaurin series and Taylor and Maclaurin approximations for functions. All right, after today's lecture, we will have two more lectures, one next Wednesday. That would be April the 25th, and then April the 30th will be the last lecture of the semester. So the 25th and the 30th are the last two lectures for the semester. All right. So let's first of all talk about the ratio test. So remember, we're talking about convergence of series. And we're going through all these different ways that you can decide on whether a series converges or not. And so where we left off last time is we were talking about the ratio test. Excuse me. Now remember, the ratio test, basically you're looking at the limit of the comparison of the n plus first term to the nth term of a series. And when you look at that limit, right? If you get that limit is less than 1, then the series, and I should say at the beginning here, we're talking about the series as n goes from 1 to infinity of a sub n. So if you take the limit as n goes to infinity of the n plus first term compared to the nth term, and you get less than 1, then you know that the series converges, and not only does it converge, but it converges absolutely. We're talking about absolute values here. And when we get that the absolute value converges, we know that the series converges absolutely. if the limit as n goes to infinity of this comparison of the n plus first term to the nth term is greater than 1, then the series diverges. And then finally, if the limit as n goes to infinity of the n plus first term of the nth term is equal to 1, then basically not enough information. You don't know whether it converges or diverges. So I'd say just not enough info. Okay, so that's the ratio test. So let's look at an example. We looked at several examples in lecture last time, but let's go back over one more example for the ratio test. And let's look at a series that is kind of messy. So we have the sum as n goes from 1 to infinity of -1 to the n. So this is going to be an alternating series times n factorial quantity squared divided by 2n factorial. So it's kind of messy. Don't forget that when you see factorials, not all the time, but when you see factorials, the ratio test is frequently a way that you can attack a series like that to see if it converges or not. So when you see factorials in a multiplication problem like this, think about the ratio test as your first line of defense for convergence. Okay, so in this problem, right, we talk about the limit as n goes to infinity of the n plus first term divided by the nth term. So remember what I started talking about last time is just invert and multiply. Right, so the n plus first term would be -1 to the n plus 1. You don't really need the n plus 1, the -1's in there because this is an absolute value, but I'll go ahead and put them in there. And then this would be n plus 1 factorial quantity squared, like that, divided by 2, and let me use brackets here, 2 times n plus 1 quantity factorial, like that. So that's a messy expression there. And then that's multiplied by the reciprocal of a sub n, because you're inverting and multiplying here, right? Because you're dividing by a sub n, which is itself a fraction. So this would be 2n factorial in the numerator, and then the denominator you'd have -1 to the n times n factorial quantity squared. Really kind of a gross expression like that. All right, so now what you need to try to do, let's see, let's go ahead. You've got some multiplication inside the parentheses there that I think you would want to do. So first of all, let's go ahead and just, because we're taking absolute values, right, what can we do? We can dispense with the absolute values because when we take the absolute value, the -1 is going to go away. Right, and so you're left with n plus 1 factorial quantity squared in the numerator times 2n factorial, like that. And that would all be divided by 2n plus 2 factorial times n factorial quantity squared, like that. All right, so, let's see. If you think about that n plus 1 factorial squared is just n plus 1 factorial times n plus 1 factorial, that would make sense to think of it that way. I think it's going to be a little bit easier. And then we have 2n factorial. And in the denominator, you've got 2n plus 2 factorial. I'm going to put that one at the very end there. And then you have n factorial squared, which would be n factorial times n factorial. So I think if you expand those exponents out on those factorials like that, it makes it easier to divide things out. So notice what happens here. You start doing the arithmetic on these factorials. So n plus 1 factorial over n factorial we've talked about this before. That's going to end up giving you n plus 1, right, in the numerator. And then another n plus 1 factorial and another n factorial. Those cancel out. Also leave you with an n plus 1 in the numerator. So you have two n plus 1s in the numerator. And then you've got this 2n factorial over 2n plus 2 factorial. So let me show you some arithmetic off to the side here to show you kind of how that works out. Now in the denominator, I'm going to put a little arrow here and put this right above it right here. The 2n plus 2 factorial, you're just counting again. So this is 2n plus 2 times 2n plus 1 times 2n times 2n minus 1, etc., like that. And in the numerator, you get 2n times 2n minus 1, etc., 2n minus 2, and so on. You're just counting down like that. And in both cases, you go 3 times 2 times 1 at the end. 3 times 2 times 1. So notice what's going to end up canceling there is the 2n, and everything below 2n like that is going to divide out. And so notice you're left with 2n plus 2 in the numerator, or I'm sorry, in the denominator, and a 2n plus 1. Everything else cancels out. So you're left with that expression right there. So that gives us the limit as n goes to infinity. If I multiply this out in the numerator, I get n squared plus 2n plus 1. And in the denominator, I get 4n squared plus 6n plus 2. And so we know, we've talked about this many times during the semester, that this kind of rational expression, when you're taking the limit at infinity, all you really care about are those dominant terms at the beginning. And so this goes to n squared over 4n squared, or goes to 1/4. And so the value of the limit in this particular problem is 1/4, right? We know that the limit as n goes to infinity of a sub n plus 1 divided by a sub n is equal to 1/4. So we conclude at the end, don't forget this conclusion. So this series converges by the ratio test. I will want to see you tell me that it's the ratio test that you're using at the end. And we're using the conclusion of the ratio test that if you get this limit to be less than 1, right, the series converges. Now remember, and we've talked, not only does it converge, by the way, it converges absolutely. I should point that out. It is an alternating series, but the conclusion is that with an alternating series, we can write that this is absolutely convergent, which means no matter how you rearrange the series terms, you're always going to get this to converge to the same number. And again, remember, we're not finding what that number is. You could certainly start looking at the sequence of partial sums and generate some terms there, and you can start getting an idea of approximating what that sum's value would be. Okay, so this is a good example of the ratio test. Not a bad little example there because it is a little bit messy. All right, let's move on to talking about the root test next. Where we saw that the ratio test was good for factorials in particular, the root test for a series works really nice if a sub n has powers of n in it. If you see lots of powers of n, then the root test is a lot of times a nice test to use. And this test, very similar to the ratio test. You've got that the limit as n goes to infinity of the nth root of the absolute value of a sub n is less than 1. If that limit is less than 1, then the series converges. And again, remember, not only does it converge, but it converges absolutely. if the limit as n goes to infinity of the nth root of the absolute value of a sub n is greater than 1, the series diverges. It does not have a sum. And you know the punchline here at the end. You know how this is going to finish. Just like the ratio test, if the limit as n goes to infinity of the nth root of the absolute value of a sub n is equal to 1, not enough information to make a decision here. Not enough info. So essentially, you're saying that the root test fails, right? Because you don't know whether it converges or diverges there. All right. So let's look at an example of the root test. So let's say we have this series. The sum as n goes from 1 to infinity of n squared plus 3n, all raised to the nth power, divided by 4n squared plus 5, also raised to the nth power. And so you see this is a classic example here of a root test problem, because you've got these powers of n here. So when you see those powers of n, you are thinking root test would be a good way to deal with the problem. All right, so we look at the limit as n goes to infinity of the nth root of a sub n, of the absolute value of a sub n. All right, so this would be the nth root of, here you'd have n squared plus 3n to the nth power divided by 4n squared plus 5 to the nth power, like that. And, you know, since the we're talking about the absolute value in there, we can assume that this expression is going to be positive. And so what we have here is that this would be the limit as n goes to infinity of simply just n squared plus 3n over 4n squared plus 5, right? The nth root cancels out, divides out with those powers of n there. And so very quickly you get an expression where you're just looking at the dominant terms, and you know that this expression approaches n squared over 4n squared, or 1/4. So our conclusion here is, by the root test, this series converges. All right, you got powers of n there, you use the root test, and it works out pretty well. All right, so let's look at one more example of the root test right here. So we have the sum as n goes from 1 to infinity of n to the n over natural log of n to the n. To the n right here, like that. So again, those nth powers would suggest definitely that this is a root test problem. So we use the root test. And so we take the limit as n goes to infinity of the nth root of n to the n, technically the absolute value of all that, over the natural log of n to the n. Right, and so you're going to get positive expressions there. And so this is going to end up giving you simply the limit as n goes to infinity. You've got the nth root of n to the n. So that's just n in the numerator. And in the denominator, you get the natural log of n. And so that's infinity over infinity. But when you use L'Hopital's rule, so by L'Hopital's rule, you get that is going to be equal to just infinity, because you're going to get a n when you do that, right? When you take the derivative of the numerator, you get 1, and when you take the derivative of the natural log of n, I mean, technically, actually, you're looking at this function, x over the natural log of x, and you're looking at the limit as x goes to infinity of x over natural log of x, and that's L'Hopital's rule. And so that gives you 1 over x, or simply just the limit as x goes to infinity of x. which would be infinity. So you get infinity as the value of the limit, and so by the ratio test, the series diverges. The series does not have a sum. All right, so another good example of the root test. All right, so now that finishes kind of going back over the ratio test, introducing the root test. And so now I'm just going to go through a general overview of series here. So what we're going to do is one last time, this will be the last time we do this in lecture, is we're going to go back through and just look at some problems that involve series and talk about what you would do to deal with the convergence of the series. This is a great review for a section on the test where you are going to be given a series, and the directions are simply going to say, use all these tests, pick the appropriate test, and figure out if this series converges or diverges. And so frequently, the difficult thing is to try to decide what test to use to try to decide the convergence of the series. All right, so in this problem, when you see a rational expression as the nth term right here, it's just a polynomial over a polynomial. We have talked about before, use limit comparison here in a problem like this. Use limit comparison and simply look at the difference and use the difference in the degrees to know what to compare it to. So use the difference in the degrees. So in this problem, the difference in the degrees is 1, so compare to the sum as n goes from 1 to infinity of 1 over n, which is harmonic, right? That's our harmonic series. And we know that the harmonic series diverges. So we're comparing to a divergent series. So when we do this, remember you're talking about the limit comparison test. So you have the limit as n goes to infinity. And you're just comparing the nth terms of these two series. So you have 1 over n squared plus 2n over n cubed plus 3n squared plus 1. Remember, it doesn't matter how you compare these, I mean, as far as which order. So in the numerator, you get n cubed plus 3n squared plus 1 when you invert and multiply. In the denominator, you get n cubed plus 2n squared. So what do you get here? Well, you get a rational expression. The degrees are the same. So this expression is going to approach the dominant terms, which is just n cubed over n cubed. That approaches 1. Remember, with the limit comparison test, if you get a constant value like this, the two series have to do the same thing. So by limit comparison, since the sum as n goes from 1 to infinity of 1 over n diverges, then the original series diverges also. Okay, so when you see a rational expression, that should be really quick and routine here to go ahead and use the limit comparison test. All right, so the next problem, let's say we have this sum. I'm sorry, this sum. The series n is as n goes from 1 to infinity of -1 to the n plus 1 times 3n plus 1 over n factorial. Now, you are interested in whether this series converges or diverges, or converges absolutely or converges conditionally. If this is an alternating series, so that is a question here. Remember, with alternating series, conditional and absolute convergence is an issue. But this does have a factorial in it. And so what makes sense to do here is to just use the ratio test. The ratio test will work just fine here in this problem because of that factorial. So the factorial tells you use the ratio test, or at least try the ratio test here on this problem. So we're looking at the limit as n goes to infinity of the comparison of the n plus first term to the nth term. Remember, that's the ratio test. And it's the absolute value there. Now, also don't forget, since it is absolute value, all that means is that that factor of -1 is going to go away here, right? And so you've got a sub n plus 1, which would be 3 times n plus 1 plus 1 over n plus 1 factorial, right? There's a sub n plus 1. And then you're going to multiply that by the reciprocal of a sub n. So that'd be n factorial over 3n plus 1. And I can drop off the absolute values here. I've already taken the absolute value of the expression, right? So let's see. Let's go ahead and see how this is going to work out. First of all, the n plus 1 factorial and the n factorial divide out. We've seen that numerous times now. And so that leaves me with an n plus 1 in the denominator. And then I also have a 3n plus 1 in the denominator as well. In the numerator, I get 3n plus 3 plus 1. Right? And if you want to clean that up, you can. You don't really need to do that, but not a problem. You get 3n plus 4 in the numerator. And in the denominator, I get, if you want to multiply it out, you can. You get 3n squared plus 4n plus 1. So it's another rational expression there. This approaches the dominant terms, which would be 3n over 3n squared, or 1 over n. And as n goes to infinity, 1 over n is going to go to 0. And so the value of this limit is 0. And so what do we have here? Our conclusion is, by the ratio test, the series converges, and it converges absolutely. Remember, the conclusion on the ratio test is you get absolute convergence if you get a value less than 1. And so this series converges. Not only does it converges absolutely. All right, so that's our second example. So we're kind of going through just a little kind of rundown of some different types of problems with series. So our third problem, the sum as n goes from 1 to infinity of e to the n over n cubed, like that, you know, and I want you to kind of keep in mind that the way expressions grow, you know, that factorials grow, you know, if you're talking about how fast expressions grow, you've got factorials kind of on the top, and then you have exponential functions, and then you have power functions, and then you have logs, like this. And, you know, this is from fastest to slowest. So notice you have an exponential expression over a power expression here. So your intuition here should be, hey, this thing doesn't even go to 0. The nth term doesn't go to 0. I should be able to use the nth term test here. So you're using the nth term test to see if it diverges, right? So you're looking at the limit as n goes to infinity of e to the n over n cubed, e to the n over n cubed. All right, so if we look at this function, f of x equals e to the x over x cubed, then the limit as x goes to infinity of e to the x over x cubed, that's just infinity over infinity. You use L'Hopital's rule, and you get e to the x over 3x squared. You get the limit as x goes to infinity of e to the x over 6x. And finally, you get the limit as x goes to infinity of e to the x over 6. And finally, that's just infinity over 6, which is infinity. And so we know that this limit here is infinity, right, using L'Hopital's rule. And so what do we know? By the nth term test, this series diverges. Okay, so that's good. So that series doesn't even have a sum. All right, let's look at another problem here. Let's say we have the sum as n goes from 1 to infinity of 3 to the n over n plus 1 to the n. All right, so the nth power is there. Would suggest the root test. By the way, you could also probably end up getting by with the ratio test as well. You can always try the ratio test on a problem like this. Sometimes it works, sometimes it doesn't. But the root test is made to order for this kind of problem. So if the limit as n goes to infinity of the nth root of the absolute value here, which is just the expression itself, because these are all positive terms. And so you get the limit as n goes to infinity of 3 to the n, no, not 3 to the n, sorry, just 3 in the numerator, and in the denominator, n plus 1. And so you get 0 there. And that tells us that by the root test, the series converges. It has a sum. All right, let's see. Let's finish this. That's 4 different series we've worked so far, kind of a little overview of a lot of different methods here. Let's look at one last problem. We'll call this one E. So this is the 5th one. And you have the sum as n goes from 1 to infinity of 3 times 9 to the 3n plus 1 divided by 6 to the 2n minus 3. I'm sorry, definitely not. Yeah, I'm sorry, 6 to the 2n minus 3. That's right. Yep. All right, so you have constants raised to functions of n power. And so that's suggesting to you that this series might be geometric. And so you want to try to put this in geometric form, in the geometric form for a series here. So let's see if we can do that. Use rules of exponents. So you have 3 times, so 9 is 3 squared, first of all, to the 3n plus 1. And then in the denominator, you get, let's see, you get 6 to the 2n divided by 6 to the 3rd, because you subtract exponents there, like in a situation like that. So that would be okay to write that. Or you could say times 6 to the negative 3 if that's, and actually maybe that's the way I'll do it. I'll write that as times 6 to the negative 3, like that. That way we're looking at that as adding the exponents, okay? And really, if you wanted to, in the numerator, I wrote 3 squared to the 3n plus 1. And I tell you what, I'm just going to leave it like that. That's fine. And so you get the sum as n goes from 1 to infinity of 3 times, that would be 3 to the 6n plus 2, divided by, and that's 6 to the 2n would be 6 squared to the n times 6 to the negative 3. Okay, because it's kind of an ugly expression here then. So you have the sum as n goes from 1 to infinity. In the numerator, this would be 3 times 3 to the 6n times 3 squared. Man. And in the denominator, you get 36 to the n. And then this would be times 6 to the negative 3. Let me get rid of that 6 to the negative 3 here. I'm getting sick of leaving it in the denominator. So I take the 6 to the negative 3 to the numerator, 6 to the positive 3. And then I also have a 3 and a 3 squared, so that's 3 cubed, or 27. And then I've got 3 to the 6n, which would be 3 to the 6th power to the nth power. And this would be divided by 36, finally, to the nth power. And then, you've got 3 to the 6th power, right? That's 3 squared times 3 squared times 3 squared. It's 9 times 9 times 9, which is 729. So you've got 6 cubed times 3 cubed. I don't really care what those are. Times 729 to the nth power. And this is all divided by 36 to the nth power. Finally, you get, the way I want to write this, and you might have thought of other ways to write this one out than I did. Maybe you found a more elegant way of doing this problem than I did. That's fine. That's what you want to end up with at the end. You want to finally end up with a constant raised to the nth power, right? And so this is geometric. Finally, we know that at the end, we know that the R value is 729 over 36, which is greater than 1. And so we know that the series diverges. We knew we were going to come up with it being geometric at the beginning. It was just a matter of having to go through all the different steps to try to combine the exponents. So lots of different exponent properties going on in that problem. All right, so what we're going to do now for the rest of the semester is we're going to go on and look at a series of functions. What we have been talking about so far are series of constants and the convergence of those constants. And so now we want to talk about series of functions instead. And in particular, the most important class that we're going to deal with here are what we call power series. And a power series is a series that it kind of follows this form. The sum as n goes from 0 to infinity of a sub n times x minus c to the nth power. And this is a power series centered at x equals c. All right, and the a sub n's are the coefficients of the terms. The a sub n's are the coefficients of the terms. And those a sub n's are going to become very important as we deal more and more with series of functions with power series. All right, now so let's talk about how these are centered. So this is a power series centered at x equals c. And notice you've got a power of x minus c in there. So if we look at this sum, the sum as n goes from 0 to infinity of, let's say, 1 over 2 to the n times x minus 3 to the nth power, then this is a power series centered at 2. I'm sorry, not centered at 2, centered at 3, sorry. Right, because it's, and actually technically you'd say c equals 3 right here. Centered at c equals 3. Right, this is x minus c. C is going to be 3 in this case. If we have the sum as n goes from 0 to infinity, let's say we have e to the n over n factorial. And this is times x plus 4 to the nth power. Then this is a power series centered at negative 4. And by the way, one thing I didn't mention here, which I definitely should have in both of these problems, the coefficients. So in the first series, the coefficients, the a sub n's, would be 1 over 2 to the n. In the second series, the a sub n's would be e to the n over n factorial, like that. All right, so let's see. Let's look at one more. The sum as n goes from 0 to infinity of -1 to the n plus 1 over n times x to the n. So since this is just x to the n, that's technically x minus 0 to the n. And so that's a power series centered at c equals 0, centered at 0. And believe it or not, it is important as to where the series is centered, definitely. All right, so if we have a series, so we've talked about where they're centered now and how you can tell that based on the way it's written. Let's look at this power series right here. The sum as n goes from 0 to infinity of a sub n times x to the n, like that. So, if you are looking at the terms here, the first term would be a sub 0, right? That's when n is 0, because then you'd have x to the 0, which is 1. And then that would be plus a sub 1 times x, plus a sub 2 times x squared, plus a sub 3 times x cubed, and so on and so forth, right? Like that. And notice the a sub n's, the a sub 0, a sub 1, a sub 2, and so on, those are the coefficients for the expression. All right, so let's look at this series. We're going to do a little bit more with this than what we've been doing. So let's say we have the sum as n goes from 0 to infinity of x to the n over n factorial. Now, first of all, that would be the sum as n goes from 0 to n of 1 over n factorial times x to the n. You'd think about it that way. A sub n would be 1 over n factorial. And this would be a power series centered at x equals 0. Okay? So now if we picked an x value here, so let's just pick an x value out of thin air, right? This is a function right here because you've got this variable in here, x to the n. So that the question is what values of x are allowed in this function. So let's write that down here, that question. So what values of x are allowed for this series? And if you think about it, that question is really what's the domain of the series, right? The set of x values that you can use in this function right here. And so the question is, what is the domain? That's really what we're asking here. So now, with that in mind, let's pick an x value. Let's pick x equals 5. So if I pick x equals 5, my sum looks like this. The sum as n goes from 0 to infinity of 5 to the n over n factorial. Right, we just substituted x equals 5 in. And if you think about that, that's the type of series we have been talking about over the last couple of days in class. And so we've got all these tests. We could actually test to see whether when you pick x equals 5, whether you actually get a sum here. And if you do, then we're going to say that that x value is in the domain. So when we pick x equals 5, we get that series, and we would probably use the ratio test here because of the factorial. And so when I use the ratio test, this is actually a pretty easy one to go through. You've got, and I don't need absolute values here because all the terms are positive. So you have 5 to the n plus 1 over n plus 1 factorial multiplied by the reciprocal of a sub n, which would be n factorial over 5 to the n. So you're talking about the limit of that expression there, and that's the limit as n goes to infinity. Let's see, we'd get 5 in the numerator and n plus 1 in the denominator, and you'd get 0. And so what do you get? You get the series converges. So the series has a sum when x is equal to 5. So what we say here is that we say that 5 is in the domain for this power series, for this function that's defined as a power series. right? And so you could go through and you could pick different x values and see if you know, which ones are in the domain and which ones are not in the domain. Now, obviously, just like any function, you don't really want to have to pick every x value that you in the real number line, right? There's too many of them to pick, and so we got to find other ways to deal with this kind of problem. Okay, so first of all, let's write down a definition and then a theorem here. So definition, first of all. The domain of the function that's written as a power series, f of x equals the sum as n goes from 0 to infinity of a sub n times x minus c to the n, right? So this is just a power series centered at c, is the set of all x for which the resulting series of constants converges. Right? When you plug in an x value for a given power series, you're either going to get a convergent or a divergent series. If when you plug in an x value, you get a convergent series, then x is in the domain. If you get a divergent series, then the x is not in the domain. Right? So you pick an x. If you get a convergent series, x is in the domain. If you get a divergent series, it means there is no sum, then x is not in the domain. All right, and then to kind of follow that up, that definition, we have this theorem. For a power series centered at x equals c, exactly one of the following is true. You have three statements here, and one of them's got to be true. Exactly one of the following is true. And it goes like this. Number one, the series converges. The series converges at x equals c only. Oh my gosh, that would be absolutely the worst case scenario here, and that would be more or less a useless function if you think about it. And you're saying that that power series only converges when x is equal to c. It doesn't converge anywhere else. And so there's only one x value that's even in the domain for that kind of power series, and that would be x equals c. So that's one possibility, is that the series converges at x equals c only. Number two, the series converges for the absolute value of x minus c less than r, and diverges for absolute value of x minus c greater than r. So now what that requires a few drawings here. We have a third condition, by the way, that we want to talk about. But before we do that, capital R, by the way, is called the radius of convergence. What this is saying is that, remember, we're saying that exactly one thing is true. And so number one is that the series converges at C only. Number two is that the series converges in what we would say is a concentric interval, a symmetric interval centered at C that has a width of R, or a radius of R. So if there's C, and that's the distance r like that, then we would say that the series converges inside that interval. And it diverges outside that interval. And it diverges out here for those x values, and it diverges out here for these x values. This is another possibility. Now notice it doesn't say what happens when x minus c, absolute value of x minus c is equal to r. When absolute value of x minus c is equal to r, in other words, the endpoints of this interval of convergence, what happens is sometimes converges, sometimes it doesn't converge. Interestingly, you have to actually check those individually. Sometimes converges, sometimes diverges. And we're going to look at some examples here so you can see that in practice, so that'll make more sense. Finally, the third condition is that the series, this is the best case scenario, the series converges for all x. And when it converges for all x, we say that the radius of convergence is infinity. The second condition, the radius of convergence is r. In the first condition, the radius of convergence is 0, when it only converges at x equals c only. All right, so let's look at an example and let's see how this works out. All right, so my example, let's look at this sum. The sum is n goes from 0 to infinity of 3x to the nth power. All right, so the first thing you want to do, this is going to be a power series, but you want to be able to identify the a sub n and the power of x separately. So separate this out and write this as 3 to the n times x to the n. So a sub n is equal to 3 to the n here, and it is centered at 0. All right, now what we want to do is we want to look at where this series converges and where it diverges. And so the test that works really nicely for power series is the ratio test. So I'm going to use the ratio test here. And let me show you how this works. So the ratio test, remember, says we're going to look at the limit as n goes to infinity of a sub n plus 1 over a sub n. So you get, this is not a fraction here at all, so you just get 3 to the n plus 1. And by the way, I have to use absolute values here because I have an x in there. And since that x could be negative, I might have negative values in there. So I can't just drop off the absolute values here. This isn't just a series of constants like we've been talking before. So this is 3 to the n plus 1 times x to the n plus 1 divided by 3 to the n times x to the n, like that. And so when you divide factors out here, you have the limit as n goes to infinity, and the 3's divide out, and you're left with a 3 in the numerator, and the x's divide out, and you're left with an x in the numerator. So you get the limit as n goes to infinity of the absolute value of 3x. Now the variable of the limit is n, and because the limit is n goes to infinity, but there is no n left in the expression. So that 3x, for any given value of x, the 3x is just a constant. And so we know that the limit of a constant is just the constant. So you just get the absolute value of 3x is the value of the limit. Now, what does the ratio test say? Remember, the ratio test says that you get convergence if the value of the limit, which we got to be the absolute value of 3x, is less than 1. And so you actually set that limit's value less than 1. And you get this nice little inequality that you can solve. The absolute value of 3x less than 1 is the same thing as negative 1 less than 3x, which is less than 1, like that. And then divide by 3, and you get negative 1/3 less than x, which is less than 1/3. And so notice that is remember where this series was centered. It was centered at 0. Don't forget what the second statement in that theorem was. That one possibility was that a series converged for this symmetric interval around C, where C is where the series was centered. Well, this series is centered at 0. And notice we got a convergence in a symmetric interval around 0. Here's 0 right here. So let's say that that's 1 right there. That's -1 right there. And so this series converges in this concentric interval around 0 that goes from -1/3 to +1/3. Notice that's what that second condition on that theorem on the previous screen was saying. Now, what we don't know is whether so by the way, that means that the radius of convergence is 1/3, because that's the distance, the radius of this interval away from 0. It's 1/3 wide, 1/3 unit wide on both sides. So the radius of convergence, r, is 1/3. That's the radius of convergence right there. Now, the actual interval of convergence, we're not exactly sure yet because we don't know what's going on at -1/3 and +1/3. You actually have to check the endpoints separately, which is kind of a hassle to do here. Sometimes this can be kind of a pain to do. So if you pick x equals 1/3, you get this sum at the very beginning. Remember what the series was. This is 3 times 1/3 to the n, which is the sum as n goes from 0 to infinity just of 1 to the n. And all that is just a string of 1s, 1 plus 1 plus 1 plus 1 plus 1, and so on. That definitely diverges. Right? And you could check x equals -1/3, which is the sum as n goes from 0 to infinity of 3 times -1/3 to the n. And that's the sum as n goes from 0 to infinity of just -1 to the n, which is -1, I'm sorry, is 1 minus 1 plus 1. That also diverges. You do get convergence sometimes at these endpoints, but certainly not in this case. So in this problem, the interval of convergence, the endpoints, it both diverged. So the interval of convergence is actually the open interval that we started with. So the interval of convergence is from -1/3 to +1/3 with parentheses, right? It's an open interval because both endpoints diverged. So that interval of convergence can, if you think about it, has multiple possibilities in general. So in general, the interval of convergence can be an open interval from A to B, can be a half open interval from A to B, or it could be a closed interval from A to B, right? It depends on the problem. And so in our case, we got a open interval, right? And that was our interval of convergence. All right, so let's see. We've got one more example that we're going to do, and then that's going to be it for power series for the day. So we have the sum as n goes from 0 to infinity of 3x to the n. So it starts off kind of like the other problem, but this is over 2n factorial, like that. And so if we want to write this one out, we would have 3 to the n over 2n factorial times x to the n, like that. And so the coefficients for this series, the a sub n's, are 3 to the n over 2n factorial. And the series is centered at x equals 0 because of the x to the n. So if we were going to find the interval of convergence, find interval and radius of convergence, right? We're going to use the ratio test to do that. This is definitely something I will ask you to do on the final exam, is give you a power series and ask you to find the interval and radius of convergence using the ratio test. All right, so this is definitely a final exam kind of question right here. All right, so the limit here, this would be a sub n plus 1, so that'd be 3x to the n plus 1 over 2 times n plus 1 quantity factorial, divided by a sub n, so it's multiplied by the reciprocal of a sub n, which would be 2n factorial over 3x to the n, like so. So we've gotten expressions like this earlier in class today. Let's see, the 3x's, I'm left with a 3x in the numerator, because there's n plus 1 of those in the numerator and just n of them in the denominator. And then with the factorials, you know, you have 2n factorial in the numerator, and in the denominator I've got 2n plus 2 factorial in the denominator. We saw that exact algebra problem earlier in class today, earlier in the lecture, and we got that in the everything canceled out except 2n plus 2 times 2n plus 1. You can expand that out again to see how that works. Now I want you to think about the fact that that 3x, again, is just a constant, and so with a limit, we could take that constant outside the limit because it's just a constant factor. And that leaves you with this limit. And as n goes to infinity, that goes to 0. So you get the absolute value of 3x times 0, and that's just 0. And so the value of this limit is always 0. And so by the ratio test, we know that this series converges always, right? So series converges for all x. So the domain for this particular power series is negative infinity to infinity, and the radius of convergence is infinity. Right, this is the best case scenario. This is a power series that converges for every x value that you can use. And that's a great kind of power series to work with when you can. All right, so that is my introduction to power series. We will finish the semester basically by looking at various types of power series. And so that's where we're headed next Wednesday and then the following Monday. So we have 2 more lectures. And we'll talk about Taylor series and Maclaurin series and generating power series for different kinds of functions. All right, so everyone have a great day. Remember, exam 3 starts Thursday. So don't hesitate to get in touch with me if you have any questions. Otherwise, you have a wonderful evening and a wonderful week. Good luck on exam 3.